Again, it's wonderful to see you all today. Today's session is on data pooling, so different approaches for pooling data sets. This picture of Max from better times when his first time snorkeling. So you'll see him a few times in this talk. So the problem, I want to start off with sort of the set of problems that you may be facing, and if this were a problem you were dealing with, this might be a potential solution. So you might have a situation where your scientific question relates to a process that occurs over the whole life course, but you only have data on people of a particular age. So for example, if you're interested in the development of disability, and you're using the health and retirement study, that study only recruits people after age 50. And so obviously stuff was happening between age 0 to 49, but you don't know anything about that on HRS participants. Or there could be a situation where the number of observations in your data set is limited. I think we've probably all been in situations where recruitment just does not go as planned. And so it's not so much that you don't have data that covers the whole life course, but you just don't have a very large data set. And the third situation that maybe this would be relevant for is where you have multiple data sets that have information relevant to your question, and you have a feeling that there might be some way you could kind of make that work to your advantage, but you don't know how, right? So you're kind of like, well, this data, I've got measures of stress here, I've got measures of stress here. Is there some way I could combine these data sets? And the answer is yes. So, but before I get to that, I want to just kind of conceptually address, what does it even mean to pool data sets? So what it means is that you're going to take information you have on some people. So let's say you have cardiovascular risk factors for younger people in one cohort, and you're going to apply it to people in to a different set of people, to kind of fill in their values that you didn't collect data on. So let's say you have example with the health and retirement study. Let's say I had so that data set doesn't start recruiting people until over the age of 50. So let's say I had a different data set that enrolled people in their 30s and 40s. Is there a way I could infer what the values of the HRS participants were likely to have been in their 30s based on what I know from this other set of people where they are in their 30s, right? So it's that sort of idea. So can any of you think of a situation where what do we do in other situations when we have observed data and we use it to fill in unobserved values?
You have like your multiple imputation kind of strategies, for example.
Yes.
And this might actually be a pooling example, I don't know, but like one of my colleagues used data from like the CPS to predict people's incomes if they were actually working when they were not working, to use it in another data set. Maybe that is actually pooling, but
no, that's a great example. Yeah. So if you've heard of or sort of are familiar with multiple imputation, then you are 10 steps ahead of where I'm going to take you today. So so if you can kind of get your head, for those of you who aren't familiar with, let me describe briefly. So multiple imputation, let's say you have a data set of 1,000 people, and let's say for whatever reason, 200 of those 1,000 people didn't answer the question you asked them on how much do you weigh. Okay, but they answered all the other information. They just didn't want to tell you how much they weigh. So the nice thing is that because very few things in this world are random, you can impute what their weight likely was with a certain degree of error around it based on not only what you know about them, so all the other variables they did answer, but also what you know about people who are like them, the 800 people who did tell you their weight. And so conceptually, that's what multiple imputation is it's filling in an unobserved value. In this case, because it's multiple, we're doing this across multiple different data sets. And I'm not going to go into all the or multiple different versions of the data set. I'm not going to go into that right now, but the point is that it conceptually, because very few things, if anything in this world is random, if I know a little bit about you, I can kind of fill in the rest. Okay, so that's the idea. That's the idea. Now, then what we're going to do today is we're going to extend that not to beyond people who are in the same study, but now to people who are not in the same study. So this is a paper that's on our on Canvas, and it will be along with these slides, which are also on Canvas. And so you'll have access to this. And if this is something that you think you might be able to use, I strongly encourage you to read this paper and then get back in touch with me, and then let's just have a conversation about how to move forward with it. But again, my goal today is to kind of give you the resources and like thinking about how this might work. So the problem that these authors were trying to solve is that we think that cardiovascular risk starts early in life, but very few cohorts have followed participants over this entire etiologically relevant period, which depending on the data set or depending on people's opinions, they even think sort of in your early 20s, you might sort of begin to see trajectories of increasing versus lower cardiovascular risk. So what that means, why this is a problem, is it means we actually have very limited information on effective prevention strategies, because when we sort of try to do prevention, we're talking about people in their 50s and 60s, and at that point the horse has already left the barn and the barn has been burned to the ground, right? So their solution is that they want to pool cohorts, and they've decided to pool these cohorts because they represent a range of different pieces of the lifespan, okay? So some are earlier, younger cohorts, some are middle-aged cohorts, some are older cohorts. I'll show you the exact cohorts in just a second. So the goal of this study was to use information from other cohorts and what we know about the etiology of cardiovascular disease to impute early and mid-life risk factors for cardiovascular disease into a cohort of older adults. So they wanted to impute what people's risk, these kind of risk factors would have been earlier in their life when they were not observed because they weren't recruited into the cohort until they were older. So they're going to impute BMI, glucose, lipids, and blood pressure, and they impute those values, these trajectories of those values, pardon me, based on things that we know are kind of either causally or certainly strongly correlated to those values, including, do you smoke? What's your diabetes status? Do you use medications, etc. So these are the 4 cohorts that they are using. So you can see on the x-axis here is the age of participants when they sort of begin, and then when they're kind of how old the oldest one is at the last observed follow-up period. So you've got Cardia, which is your earliest cohort, MESA, the cardiovascular health study, and then the oldest one is the health ABC study. Okay, so from all of these cohorts, they're going to impute, even though none of them covers the entire lifespan, they're going to impute the values across this whole time period. So if you wanted to do something like this, what would you need in order to do it? So the first thing you would need is similar, if not outright identical measures across the cohorts, which then you must operationalize in an identical way, okay? So that means, so for this example here is how they coded smoking status. So for those of you, I mean, if you've used other people's data, you know that there are probably 5 or 6 different ways that people code smoking status, okay? They might say, have you ever smoked a cigarette, even a single puff? Have you smoked at least 100 cigarettes a day? They might just say, do you smoke? With no additional, clarification. So if you have all of those, if that's the world that you're living in, you have to kind of figure out, okay, well, how do I make that consistent across the different cohorts, because that's what I need to use to then impute across everything. So here you can kind of see, you know, if there was then of course smoking is a situation where you can have a change in status. Sorry, I'm looking at my screen here, but I've got the giant screen here, so I'll turn. You don't have to like see me squinting my eyes here. So again, so this is the kind of logic you'd have to develop in order to make it so that your variables were operationalized the same across the different cohorts. This is very similar to when people say they're going to harmonize data sets. This is a similar idea. Okay, so that's another kind of literature that may be helpful if this is something you think would be helpful for you to start thinking about. So again, what their main goal was to impute cardiovascular risk factors earlier in life course, beginning at 20 years, for these participants who had follow-up data beginning in mid and late life. So for example, you might have a MESA participant, and here's just 8 random participants that they selected. And what they're going to, cardia, they're not, So there's 8 different participants, and you can see that the dots are the observed data, and the lines are what they are predicting. So if we went to participant 3, for example, we see these are the 6 trajectories they want to impute: cholesterol, systolic blood pressure, diastolic blood pressure, LDL to cholesterol, glucose, and BMI. We have 5 observed values of those for participant 3. Okay, you can see those 5 dots are of green are the 5 observed values of their cholesterol. Okay, and then based on that, they then fill in the trajectory, or sorry, based on that, plus what I know about how smoking relates to these variables, what were the other things they looked at? Sorry, do they have diabetes? Do they have hypertension, right? So those are the things that are going into saying, what would that person's value have been when they were in their 30s? And participant 3 is a person who's extraordinarily stable, you know, over these 5 time points, for example. But then you can see other situations where there's more variability, and you sort of see that you know, so I'm trying to think of an example, like participant 5 in particular sort of seems to have a lot more variability in the cardiovascular health study. And, but this is what they're generating. And then I guess I should say similar to back up. Let me pause here and just make sure everybody understands are there questions about this, what we're looking at here? And I know this is a lot. Again, my goal is really just to kind of get you the conceptual, what is the point that problem we're trying to solve here.
So I get the point, and like what we're doing with the data pooling.
Yeah.
My only question would be, like, if I'm looking at this and thinking of how we're doing it, where you're using a different cohort to predict another cohort, like what would be the answer to the question, like, for example, for participant 8, right? Like, how do we know about, like, their experience with social determinants of health and how that cohort compares to the other cohort? How do we know, like, what an individual's life was like earlier that may have impacted this kind of health? Like that's kind of where my mind goes, is like, I see the prediction, but then how do you answer those kinds of questions?
So I think that's a great question. And what I would say is that you could, so what they chose to use to impute those trajectories is just this kind of stuff, like just smoking, diabetes, hypertension, like very biomedical individual level variables. That's what they used to predict those trajectories. You could say, well, that's not actually what I care about. What I care about is how, even perhaps, how good was that prediction given different social determinants of health, right? So I think you could use this idea to test different hypotheses. So for example, perhaps you believe that people who have a big shift in socioeconomic status over their life course. So people who grow up in maybe a higher poverty household and then end up in adulthood in a middle class or low poverty household, maybe you believe that their trajectory is going to be a lot more variable, than other. You could test that using this idea, but they did not do that. What they've done here is simply say these factors, which are indeed extraordinarily good predictors of the things they want to predict, right? Like your diabetes status is as good a predictor of your sugar as there could be, right? It's because it is in some ways, like it is the same thing, you know what I mean? So of course it's not like surprising in some ways that they get it right, but this is actually your question is illustrates this tension between prediction and prevention, right? So what they are trying to do is fill in the values for participant 8. Who was only observed starting in their 70s. They're trying to predict what that person's value was in their 30s. But even if I can predict it, that does not mean that this model is telling me what I could have done to prevent them from having cholesterol like in the high 200s, right? So I think that's the other sort of tension there. And this is also a critique of like data science approaches in general, for example, which are built on prediction, but don't actually tell you why. Like we don't know why participant 8 is different than participant 3. Nothing in this table or this paper will tell us that. But now at least I know, I have a reasonable guess as to what the values of participant 8 would have been in their 30s. And so if I find somebody in my data in their 30s who's got levels, in this case cholesterol levels that are about 200, I don't know what the y-axis is here. These are not all measured on the same scale, so I don't know why they would all be like BMI is not although it looks like BMI is all down. Maybe they are all. Sorry, it would help me to have had the legend on this slide, but that person's also going to have high cholesterol in their 70s. And maybe that's not actually surprising or even very informative, which is, I think, a reasonable critique. If we had more variation, which I believe we do, yes, here which I'll go back to the slides before this slide in a minute. Here, well, now we have sort of a different story, which is how do I've got a situation where, for example, with diastolic, or the diastolic blood pressure, where the white woman and the black woman represented here kind of start at similar levels in their 20s, but have very different diastolic blood pressures in their mid 50s, right? That curve, the slope there is very different. And so now the question would be, what makes those slopes different? Now that I have the whole life course kind of filled in through my imputation, I can start to answer those questions in a much more informed manner than I could by just looking at people in their 60s or 70s. Does that kind of help a little bit, Carrie?
Yes.
Yeah.
Mm-hmm. Thank you.
Perfect. Thank you. Okay. So let me tell you a little bit about how, and again, I'm not going to go into the weeds here right now, but let me tell you about how they pooled the data from these cohorts to estimate their trajectories. They used what's called a linear mixed model. A mixed model, for those of you who are not as familiar with this, is simply just one that has both a fixed and a random effect. And then, of course, I love it when people just move on from there. And I'm always like, what is a fixed effect? What is a random effect? So a fixed effect is a parameter that does not vary. So, and by that I mean, we just assume that there is some true regression line in the population, which we call beta. And we use our data to get some estimate of that, which is beta hat. That's typical, right? And then from that sample, and that beta hat varies from sample to sample because that's just the way sampling probability works. So that is, we assume there's some value for a fixed effect. We assume there is a population parameter value of this beta. And by that, the beta, of course, is the regression coefficient. So let's say for every 1 year increase in age, my blood pressure increases by, the beta is 0.5 or something. So half a point of millimeter of mercury per year. That would be a fixed effect. A random effect is a parameter that itself is a random variable. And by that, I mean, we say there's not an average beta, like an average population beta out there. There's not a single value, but instead there's a range of values of the population beta, and there's variation around it. And I can, that some people, so I'm not just looking at sampling variability, but the reason that people differ on this value is because there's actually multiple different, there's not just one average population effect. So what they used in this study is they used a random intercept, and then they had a random effect on age. And again, what that means is that they don't assume that there's a single effective age across the entire lifespan, but instead they are treating age as a random variable where there's not one value of age on blood pressure or one value of age on glucose, but rather there's a distribution of effects of age on blood pressure, and people differ on where they fall on that distribution. Some people have a very strong age effect, and some people have a much weaker age effect. That's what the random effect allows to happen, versus the standard linear regression that you fit when you were taking Stats 101, which was everybody had the same effect, and it was 1 unit increase in age equals an expected increase in blood pressure of this, right? And like that, it was just a very kind of constrained model of how the world might work. And this is a great resource here on random and fixed effects. And I also think there are excellent courses at ICPSR that I can recommend on this kind of modeling approach. So I'm gonna skip here. Well, no, I'll tell you this, and then I'm gonna get to the most important part. So these linear mixed models were used to estimate what they called BLUPs, these best linear unbiased predictions for each person in the pooled data. And then they used these to create what they called time-weighted averages. And a time-weighted average is simply a value that is kind of, you can think about it as a kind of linear spline where the value is 0 before a certain point, it's time dependent within the point, and then it's fixed after the value. And this is not, so for an example, if somebody, the time-weighted average for a person during the 40 to 59 age interval would be 0 at all their ages before 40. It's the average of their values from 40 to 45 at age 45, and then it's the average of the values of 46 to 50 from 46 to 50, right? So across these different age period, or across these different points within the 40 to 59 age interval, and then it would just be fixed after age 50 at some value. None of this like technical stuff these are choices they made to I think impose some constraints on the data, because otherwise they were just kind of it was all gonna be like the giant spaghetti plots that were kind of uninterpretable. Using that approach, they get these time-weighted averages for their these cardiovascular risk indicators. these are the time-weighted averages at specific time intervals, so 20 to 39, and then 40 to 59. And then this figure, which I already showed you, is what that looks like now when I, instead of just looking at the average value, if I plot the predicted value for each age across these 4 groups. And now what I'm also showing you is the black line is the complete imputed value, okay, across all ages. And the dotted lines, the colored lines that are here, are each representing the observed datas that are going into that black solid line. So MESA, as you can see, covers a very long range of the lifespan for the observed data. But and then you can look at the light green line, which is the cardiovascular health study, which is only people in their 70s and older, right? And then the healthy ABC is even shorter, right? The orange line there. So at the end of the day, I get the black line by taking information from the studies that have gone into it. So, and then part of the reason I chose this paper for our data pooling kind of discussion is because they do specifically pull out the, these groups by race and gender, and that they are able to do that because of their sort of choice of data sets that go into it. They could, if, for example, if they had used the health and retirement study, this would not really be a reasonable thing to do, because the health and retirement study has a very does not have a large, certainly not older cohort. The versions from the 90s did not have a large sample of African Americans, and so they wouldn't have even been able to do this with any degree of precision. There are a couple other ways there. I want to talk about, in the couple minutes that I've got left, I want to talk about a couple other types of pools. So that's one type of pool, which is this imputing across different data sets. Another type of pool is you're going to predict into a different data set. So the steps here, you find a data set that has a data, again, on a similar measure as the one that you're hoping to fill in information on. So I've got 2 data sets, they have similar measures. This one is missing data on X, this one has data on X, and then the rest of their variables are very similar. I build a regression model in this data set that has X that I'm going to use to then generate a prediction model to fill in X in the first data set that I wanted. I'm going to show you an example of this. I'm sorry, I'm not trying to be too abstract, but I'll show you an example of this in a second. So I'm going to take the data set that has all the information I want, but not the people I want. I'm going to build a regression model, just a logistic regression model. I take the betas from that logistic regression model to build a prediction model. I then append these 2 data sets together, and then I'm going to fit the prediction model on the entire sample. So that includes the data, the actual people that built the logistic regression model and the people I want to apply that data to that don't have information on this variable I care about, to fill it in. So it's not multiple imputation. I don't do this 5 times. I just do this once. So why would I ever do this versus the multiple imputation approach? Well, you might have a situation where you have systematic missing data on a variable of interest that something like multiple imputation is just not appropriate for. And the example I'm going to show you in a second is a situation where some of the respondents in this first data set that I'm interested in were simply just not asked a question because of like a skip pattern in the interview. And that is the situation that I'm going to show you in a second. So it's not that they just didn't tell me about their weight. They decided not to answer the question. It's that for some people, I just didn't even ask them about their weight. And I did that in a very systematic way that would be a problem for multiple imputation, okay? So when is this an appropriate solution? It would be appropriate when I have an external data set, again, that is sufficiently similar to the one you're working on in terms of population scope, and most importantly, the measures, but it does not have that same missing data problem that you're trying to solve in your first one. So let me show you an example of what we did. So this was, we wanted to know what is the prevalence of passive suicidal ideation among older adults in the United States. The problem was, I wanted to do this in the health and retirement study, but the health and retirement study only asks people if they've experienced passive suicidal ideation, if they first agree that or if they first tell me that they've already felt sad. Okay, so what you can see in this little kind of flow chart at the top is that everybody comes into this part of the questionnaire, which is called the CD, the Composite International Diagnostic Interview. 8.9% of them said they felt depressed. 91.1% said they did not feel depressed. The people who said they were depressed were then asked, have you felt suicidal or not, right? And 67% of the people who said they were depressed also said they felt suicidal. But if you said you were not depressed, you were never asked the questions on suicide at all. Like there's just completely missing. So 91% of people in the health and retirement study, I have no idea what their answer would have been to that question, okay? And it's built, of course, on the logic that the only people who feel suicidal are people who also feel sad. And that, of course, is not true, but that's the logic that is underneath this skip pattern, okay? So what we did, our solution was we found an external data set that does not have the same skip pattern, but does have almost identical measures of the depression and the suicidal ideation. And that data set is the Baltimore ECA study, the Baltimore Epidemiologic Catchment Area Study. It uses an instrument that is the predecessor to the CD. It's called the Diagnostic Interview Schedule, where their measure of depression asks all questions about depression to everybody in the sample, regardless of whether or not you felt sad. So I know suicidal ideation unconditional on depression status in the ECA. I don't know suicide I only know suicidal ideation conditional on depression status in the HRS, and I'm going to use this prediction model. So what I did is I used the ECA to generate the predictors of suicidal ideation among people who are not depressed in the ECA. I just fit a linear regression model. I then took those beta coefficients and first I appended the ECA to the HRS, and then I used the beta coefficients that I had from the ECA by itself to kind of pretend that, oh, I just forgot to ask people in the HRS this question. Let's see what they would have said, and I get a general, and then I'm able to predict what that value of not depressed, but yes, suicide would have been in the health and retirement study. And this paper, I'm happy to send this paper as well. This isn't the one I asked you to read, but we published this last year. The other types of pools are meta-analysis, which I think many of you are familiar with. Again, this is a quantitative formal design used to systematically assess the results of prior work, but this is another type of pool. And the ideas that kind of go into it, we don't necessarily think about as trying to fill in information, but it is trying to fill in information. And that information is the fact that different studies sort of have different strengths and limitations, and how do I come to a better approximation of the true value, given that these studies have different sources of strengths and limitations. Another example of pooling that you may have already done is appending cross-sectional panel surveys. So NHANES, the MEPS, there's several other data sets that are designed to be appended, and NHANES is one of them. the reason why you would want to do this is to increase statistical power. But the reason you can do it is because the items in NHANES are asked the same of every year. So smoking status is always asked the same way. So when I stick last year's NHANES to this year's NHANES, I don't have to worry about are the measures consistent, because of course they are, because they were designed that way. So that's just another example of like pooling that's a little bit maybe more familiar. Yeah, 2 more slides and I'm done. So just some types of problems that pooling does not solve in and of itself. So it does not solve differential attrition. It is still the case that healthier people are much more likely to stay in your study over time. It doesn't solve survival bias, that healthier people are more likely to make it into old age, which is where your study might begin. And I think this is also to Carrie's question earlier, that pooling may inadvertently smooth out meaningful variation. And this is also true of multiple imputation in general, right? So multiple imputation is by design smoothing things out. And that variation may be important. So to summarize, again, the fundamental idea of pooling data sets is that you can take information from one study and use it to fill in the gaps in another related study. There's lots of different variations on this theme, but they all stem from the idea that the data you have can be used to impute the data you do not. But like all imputation strategies, these approaches can address some sources of bias, but they come at a cost of precision, and they also may kind of wipe out some meaningful variability. And the last slide is just this paper that is on Canvas, the Hazuri paper. And then here's another paper that I'll put also on Canvas that talks about sort of different type and kind of a much more cautionary tale, I guess I would say, in terms of different ways to pool data. So I'm going to stop sharing my screen and see sort of how questions, and I know we're at time, but I'm happy to stay. If will you, and Monica, will you stop recording now, and then that way we'll have the recording, and then we